Okay, so what this thing is, so it's called EnRoads. EnRoads stands for Energy Rapid Overview and Decision Support. So energy is basically implying that climate change is a problem that has to do with our energy sources, whether they come from fossil fuels that emit CO2 or from other sources that do not emit CO2. And then rapid overview and decision support is just kind of technical jargon for you can kind of test different scenarios as far as our energy system is concerned very rapidly and use that to support decisions on how best to deal with climate change. So this calculator or simulator was developed by MIT scientists, Massachusetts Institute of Technology, and this nonprofit organization called Climate Interactive. And it looks kind of like, you know, this kind of simple toy. You kind of slide things around and things change up here. But it's actually it's a really sophisticated model. And so it's been used to support decisions at the very highest level of government. So when the Paris negotiations were going on, tools very similar to this from Climate Interactive were used to inform John Kerry, the Secretary of State at the time, as well as John Holdren, who's major science advisor to Barack Obama. And so these tools were used to just show, okay, quickly, what would happen if we were to do X to renewables? What would that mean in terms of temperature, that type of thing. And so this is basically like as sophisticated as the most advanced models used by the IPCC, the Intergovernmental Panel on Climate Change, and the International Energy Organization, but it's just stripped down a little bit so that it can be run in a browser. But it's a very cool tool to have handy so that you can kind of test, you know, what makes a difference. Like that's kind of the whole point of this, is that you'll hear a bunch of different solutions thrown out there in the media and articles, and you know, various people will have different ideas as to what should be done about climate change. But this will help you actually see, okay, does that make a difference? And this is like a global model. So this is not thinking about necessarily your local community or the city level or the state level or even the country level. It's like global, and it has to be global because it's a global problem. Our CO2 emissions, as we talked about in the review for the test, you know, they are well-mixed greenhouse gases, CO2 is, and so it spreads globally, and so you need a global solution. So this calculator kind of allows you to be a global dictator and implement policies at the global level, which, you know, there is no global dictator, but it would be like if you were in charge of the United Nations negotiations and were able to advise, here's what the policies should be for all the countries that are coming together to sign some agreement to address climate change. So yeah, it's a really cool tool. There's like 38,000 equations embedded in it. And it's like a climate economic model, energy model, where it's, you know, if you do something like, I'll just show you something real quick. If you tax coal very highly, if that's a policy that you want to implement, what the model will do is it will find the least cost energy portfolio to supply energy to humans. And so everything changes when you tax coal. It's not just that coal will change, everything changes responding to the price pressures put on coal that you just put in there. So I will just give you a tour first of everything that's going on here. Okay, so if you click this home button and this reset button, that gets us back to our baseline, what they call business as usual scenario. And so the business as usual scenario is kind of imagining that there's no climate policy, there's no, Paris Agreement, there's no implementation of policies at the state level or city level, or all the things that actually are going on kind of are imagined not to be going on. So, for example, like Microsoft has declared that their policy is that they're going to be carbon neutral by 2030, and then remove all the carbon they ever put into the atmosphere by 2050. So these types of goals are not included in what this is calling business as usual. So we can think of business as usual here as kind of a pessimistic progression going through the rest of the century that we hopefully are not on, that we're already not on this bad of a business as usual scenario. But it's always really difficult to predict the future, and so you just kind of don't know actually like what business as usual would be going forward. But the business as usual case here, this is showing temperature going forward. So year 2000 to 2100, this is global average temperature. You can see it's kind of a very straight line, and a lot of the graphs we've seen before with actual global average temperature is more wiggly. So it's like kind of evening that out, spreading that out. You can kind of think of this as like a 20-year average maybe. But we are, we're, at 1 or above 1 degree Celsius above pre-industrial levels. So this is all relative to pre-industrial in 2020. And then they have us in this business as usual scenario ending up at 4.1 degrees Celsius by 2100. And then you can see on here, what's also put on here are the two articulated goals of the Paris Agreement, which we'll talk more about in a couple meetings from now. So they have us passing this 1.5 degree threshold in the 2020s, and then the 2 degree threshold in the 2040s, and then making it all the way up to 4.1 degrees. So this would be quite a lot of warming. This is a very, pessimistic scenario in terms of how much warming we'd get by 2100. So 4.1 degrees Celsius here is 7.3 degrees Fahrenheit. But then we also talked about how if you wanted to convert that into a temperature over land, you would also multiply it by like 1.5. So this would be something like 11 degrees Fahrenheit warming over land by 2100. And so that would have a lot of negative consequences. So we're trying to flatten this curve, if you will. We're trying to bend this temperature amount down closer to these Paris goals. And so over here, it's showing you kind of what's driving this temperature increase. And so that is our global sources of energy. So we talked about at the very beginning of the class, what's supplying our energy still, and it is still fossil fuels, right? So we have the majority of our energy coming from oil here. The red line is oil in 2020. And then we have coal, and then we have natural gas. So our three fossil fuels are our primary energy providers. So about 80% of the energy humans use still comes from fossil fuels. Then we have bioenergy, which we talked about earlier in the class, is mostly like wood for stoves. So it's especially, used heavily in the developing world still, that most of the cooking is done with wood. And so that's another source of energy that's releasing CO2 when you burn wood. We have nuclear in light blue down here. So nuclear does not produce CO2. So that's has other, it has other problems when it comes to what you do with the waste and all that, but it doesn't produce CO2, so it's good global warming wise. And then we have renewables here in green. So renewables, wind, solar, hydroelectric, they are growing, and you hear a lot about how fast renewables are growing, but they're growing from a very small baseline. And as far as this model is concerned, with the business as usual scenario, renewables do not take over any one of the individual fossil fuels by the end of the century, just by themselves, without you kind of manipulating things down here. So we have, yeah, we just have coal growing and growing and growing. We have natural gas growing and growing. We have oil kind of peaking as we basically like kind of run out of easily extractable oil, and then coming down towards the end of the century. But still, fossil fuels dominating by the end. And so that's why you still have temperatures rising throughout the entire century. And we can change this graph to, for example, CO2 emissions by source. And so we see, for example, yeah, coal is the dominant emission of CO2 throughout the remainder of the century, and then oil and then natural gas. Okay, so let's look at the levers that we can actually manipulate here to change this, to bend this down. And what's very cool about this model is that you can do a lot of stuff very quickly. So you can move sliders around and see their results very quickly. But you can also go into a lot of detail. So if you click on this vertical ellipses, these dots, on each one of these things, it'll open up a lot of details on those things. So it will give you a bunch more kind of advanced options that you can play around with, other than just like for coal, very highly taxed versus subsidized. You can do a lot more detailed manipulation. But then in this panel, if you click on this I, which I think stands for info, it'll give you a bunch more information. So they have examples of what manipulating coal taxes would do. So yeah, government policies that phase out power plants or make them more expensive in any way, such as taxes on coal. Financial services industry like banks or global development institutions like the World Bank, limiting access to capital for new coal mining, refining, and power plant infrastructure. So these would be examples of like a tax on coal. And then it tells you various things about what the model does when you tax coal and kind of interesting dynamics that you might see. It also talks about these so-called co-benefits. So like if we're going to tax coal, we're primarily doing that in this model because we want to reduce the CO2, the greenhouse gas portion of the power production. But that's also going to have other benefits. And you probably read about this in the Wizard and Profit book, where they talk about coal and how reducing coal emissions is also really beneficial in terms of air pollutant reduction. So coal emits sulfur dioxide, which is very harmful to human respiratory systems. And so if you were to eliminate coal, you get the greenhouse gas benefit, but you also get improved air quality because of that. So that would be a co-benefit. It's like another benefit in addition to removing greenhouse gases that you would get from removing coal. And then they also talk about equity considerations, how a policy could disproportionately affect low income versus high income communities. And then it will also give you the details of what these descriptive words mean. So what does very highly taxed actually mean? It gives you this number here, and it gives you like a range of what they consider to be very highly taxed, taxed. And then like what that would do to the cost of energy, for example. So each one of these levers has this type of information in it. And so it's a great resource for you to just kind of look quickly and see like, okay, what is actually going on with these levers? What do they mean? What does very highly taxed mean? What exactly what would be an example of this in the real world? That type of thing. So there are 18 of these levers here. And so this is basically all of the solutions to global warming that you might hear about are embedded in these 18 levers. The ones that wouldn't be would be anything that's a adaptation rather than a mitigation. So mitigation means you're eliminating greenhouse gas emissions and so getting less warming, where an adaptation means that you're kind of allowing it to warm, but you're going to adapt society. So like building a seawall would be adaptation, where mitigation is reducing greenhouse gas emissions so that the seas don't rise and you don't need to build a seawall. So it doesn't have adaptation in here. This is all about mitigation. It also doesn't have geoengineering, really, unless you consider this carbon removal stuff geoengineering. But yeah, so like anything that's like about, for example, increasing the albedo of the Earth by putting aerosols up into the stratosphere and reflecting more solar radiation back to space, that would not be in here, because this is all about eliminating warming by reducing greenhouse gas emissions, not by canceling it out through some other means. So anything that's about reducing greenhouse gas emissions should be in here in some way. So let's go through each one of these 18 as a tour. So we just talked about coal, oil, natural gas. So those are our three fossil fuels. So we have coal is it's part of our electricity system, not so much in California. In fact, we don't have any coal power plants in California anymore, but through a lot of the world, it still is, especially India and China are still building a lot of new coal infrastructure. And so that's why they have this continuing to be a dominant energy source throughout the rest of the 21st century. Oil, so oil is refined into gasoline. So that's our main transportation fuel. So all of our cars that are internal combustion engine cars, so any car that's not electric is going to be using oil. And so that's why that's such a dominant one. And then natural gas is now the #1 source of electricity in the United States. And natural gas is methane, but it actually emits CO2. When you burn the methane, it emits CO2. And so natural gas is producing a lot of our electricity, but it's also, part of our energy use in other ways. So for example, in my house, I can think of at least 3 ways that I'm using natural gas. Gas stove, water heater, and just regular heating is coming from natural gas. So I'm using electricity that largely actually comes from natural gas as well. It's just a natural gas power plant that's producing electricity, and then directly natural gas that I'm burning in my house. And when I burn that natural gas, it produces CO2, even though the natural gas itself is methane. So when we talk about methane emissions in the form of CH4, which is the molecule of methane, we're usually talking about methane emissions from like agriculture or, pretty much agriculture. So that's like from cows burp methane, and so that's a big part of the methane emission. A big part of methane emissions, as well as methane released from anaerobic bacteria in like landfills. So bottom line there is natural gas is methane, but when you burn it, it turns into CO2. And so these are our three fossil fuel components in our energy supply. And then we have bioenergy. So this one, as I said, was like mostly wood, but we also can put into here like ethanol. So if we're gonna grow corn and turn that into a fuel that we can put into cars, that would be in bioenergy. And then renewables so they put all renewables just in one category here. So we have solar power, geothermal, wind, as well as hydropower, hydroelectric dams. So that's all in this one category of renewables, but it's mostly going to be solar and wind that are the dominant contributions to renewable energy. We have nuclear energy here. So the difference between coal, oil, natural gas, and bioenergy is that these fossil fuel sources, remember, are taking carbon that's buried underground and sequestered from the ocean atmosphere system and putting that into the ocean atmosphere system. So that was like that diagram that we showed with the carbon cycle with all the little kind of atoms running around. And bioenergy is kind of taking carbon that's in that ocean atmosphere system and using that for energy, but it's not actually introducing new emissions into the system. So it's kind of like, so if I move this around, it doesn't actually change temperature hardly at all, because we're not actually introducing new carbon into the system. And then we have, yeah, so then renewables and nuclear are both carbon-free sources of energy. So those are, the more you increase those, the less temperature you're going to get. And then we have new technology. That's an interesting lever there. So discover a brand new cheap source of electricity that does not emit greenhouse gases. Some speculate that such a breakthrough could be nuclear fusion. So all of our nuclear power plants are currently nuclear fission plants, or thorium-based nuclear fission. So instead of using uranium, using thorium as the molecule or as the atom. So these are both kind of derivatives of nuclear energy that people have hopes for. So some new technology comes along and helps us displace fossil fuels. So that's that category. So we have 1, 2, 3, 4, 5, 6, 7 categories of energy supply over here. And then carbon price gets put into energy supply, probably just because it didn't have a home anywhere else. But a carbon price is just like a tax imposed kind of on all production or any type of economic activity that produces carbon dioxide. So it would be, it could be directly on the power plant for producing carbon dioxide, or it could be imposed on goods and services at the level of the consumer. So it's like you're paying kind of an additional sales tax on goods that have particularly high carbon footprints. But it's just something that would be like a dollar amount per unit of CO2 released for some type of a good or service. So that's going to, the higher that is, the less temperature you're going to get later in the century. So those are our energy supply categories. Then we have transport and buildings and industry. Both of these have 2 sliders associated with them. So energy efficiency and electrification. So what would be an example of increasing transport energy efficiency? What does that mean? So you'll hear about like the fuel economy or miles per gallon, right? So anytime there's something that's talking about efficiency, you have like a rate, you have like something that you want divided by, your cost or like what it takes to get that. So for energy efficiency, for transport, it would be like increasing the miles that you get for every gallon of gasoline. So if you double the miles you get per gallon of gasoline and you don't increase the miles that you drive, then that's like having the amount of gasoline that you would use. So that's good in that sense. What about electrification of transport? So that's buying or switching over cars from gasoline burning cars or internal combustion engine cars to electric cars like Teslas or Nissan Leaf. There's various electric cars coming out. Okay, what about buildings and industry? So what would be, how could we increase the efficiency, the energy efficiency of a building? So better insulation, yeah, that is increasing energy efficiency. So that means that you're getting more of your comfortable temperature from less energy. Yeah, LED lights is a great example too. So that's, you're getting just as much light from less energy. So if you have one of those old-fashioned incandescent bulbs that's 100 watts, that means you get a certain amount of light for 100 watts of energy. So 100 joules per second. Where an LED light is something like 1 watt for the same amount of light. So it's more efficient, same amount of light for way less energy. And same with insulation, that if I have a much better insulated house, then I can get the same amount of time at, say, 72 degrees Fahrenheit for much less energy, because I'm not losing all of that heat through my doors, cracks in the walls and everything like that. So those are like the main examples: lighting and heating for energy efficiency for buildings. And then this is an interesting category: growth. So we've talked about this in the context of the Wizard and Prophet book a lot. So we have population growth. So you can imagine population goes up, then we have more people consuming more goods and services, and so temperature will go up. And then economic growth is also going to have this effect on temperature. And so this gives us an excuse to go back to our friend, the Kaya identity. So they have the Kaya identity in here, Kaya graphs. And so before, we looked at this just in terms of the equation itself, but now we can actually put numbers on it. So remember how I had CO2 emissions equals. So here are our CO2 emissions in gigatons of carbon per year. Remember, CO2 emissions are the flux into the atmosphere. Concentration is the amount in the atmosphere. Concentration is the bathtub, is the level of water in the bathtub, where emissions is the flow through the faucet. So CO2 emissions equals are 4 different components. So these are the same things we talked about before. So there's global population. So global population is increasing, but the growth rate is decreasing. And so that means that that global population is expected to level off. In the Wizard and Prophet, I think they talk about 10 billion people by the end of this, or maybe they talk about 10 billion by mid-century. So this is about the same as what they say in that book. And then kind of 11 billion people by 2100. So population increasing by still, like 40% through the end of the century. And then GDP per capita just kind of exploding. So that is a big, this really shows like where the headwinds come from. Like why, as you start manipulating these levers around in this calculator, you'll find that it's very difficult to reach the Paris agreements. And the reason why, the primary reason why, is these 2 graphs here. It's this global population and GDP per capita that are both going up. And so when we come back, when we look over here, these are both going down. So these are both in the good direction in terms of global warming. The energy intensity of GDP, that's how much energy it takes to produce a given amount of goods and services, remember, and then the carbon intensity of energy, how much CO2 is emitted per unit of energy. And so these are both coming down, these are good. But these are going up, population and GDP per capita. So it's not, of course, it's not bad for GDP per capita to come up, especially considering when, we have like over 1 billion people with almost no access to electricity or running water. You want GDP per capita to come up, especially in the developing world. But because all of the goods and services that we use require energy to produce, and because that energy is still coming from fossil fuels mostly, this makes it really hard to bend this curve down of emissions. So really what we primarily need to do is to eliminate this carbon intensity of energy. This needs to be coming down a lot faster. So we have less CO2 going into the atmosphere per unit of energy. So an example of that would be switching from coal to renewable energy so that you can get your energy without releasing CO2 into the atmosphere. But this also shows why if you think about it, like so the Industrial Revolution happened in, 1800s, and we've had all of that production of goods and services over that time period. And through all of that, by the year 2020, by right now, we've only seen 1 degree Celsius rise in temperature. And now all of a sudden, looking through the next 80 years, we're talking about an additional 3.1 degrees Celsius rise in temperature in this model. And it's like, where is all this? Why are we getting 3 more degrees over the next 80 years when we've only had 1 degree over the past couple hundred years? And the reason is because of this increase in population and this increase in economic activity that's just so energy intensive. There's so much more energy expected to be consumed over the next 80 years that's what makes the acceleration of the temperature like that possible. And so what we're really trying to do is get the energy, get the GDP without emitting CO2 into the atmosphere. And so in order to do that, you have to eliminate the fossil fuels and get to renewable sources of energy, or capture the CO2 from the fossil fuels before it is emitted. And so let's just go to our last couple over here. So land and industry emissions. So deforestation is one. So if we were to reduce, so I'll go back to home, reset graphs. If we were to reduce deforestation, then we're going to get a little help with temperature. And then everything that's not CO2. So this model really focuses on CO2 emitted because of our energy sector. And so the other major anthropogenic greenhouse gases are methane and nitrous oxide. And those are in this methane and other gases lever here. And so if we were to get those down, then we are also going to be reducing temperature by the end of the century. And then we have one last category here, carbon removal. So afforestation is the opposite of deforestation. So that's like planting trees. And then there's technological. So it's basically saying, okay, how do we remove carbon from the atmosphere? We can either do it naturally by planting trees that sequester carbon. That's our photosynthesis equation. They take in carbon and they use it to make their structures. Or technological, where you have some type of a major industrial machine. So one of the phrases that gets used is bioenergy, carbon capture and storage. So that would be like planting a bunch of crops that take in CO2, using those crops to produce like ethanol, burning the ethanol, but capturing the carbon, the CO2 before it leaves, and concentrating it and injecting it underground or something. So you're using bioenergy, but you're capturing the carbon before it goes into the atmosphere. And so you're actually like sucking CO2 out of the atmosphere because it ends up in the ground rather than in the atmosphere. So that would be another way, is that once you have carbon in the atmosphere, you can try to get it out some way. Okay, so any solution that you think about with climate change should fit into this, as long as it has something to do with reducing greenhouse gas emissions. So I will show you some ways that this calculator is useful. So as I said, there's like 38,000 equations underlying this. And so that means it's going to show you things that are not necessarily intuitive, or it's going to give you insights that you wouldn't have otherwise. So let's look at potentially one of those. So if I go to transport here, and I move this electrification bar to very highly subsidized, or I guess it's not going to be subsidized. It's going to be just encouraged, yeah, or incentivized. So if I move this to highly incentivized, what do you think is going to happen over here to these lines? So think about like each one of them individually. So if I move electrification of transport, so that's like I'm changing the cars on the road from gas burning cars to electric cars like Teslas. What happens to each one of these energy sources? So we have coal, oil, gas. So let's start with oil. What happens to oil, do you think? So you should always simulate these things in your head and see if what happens in the calculator makes sense to you. And if it doesn't, then that's good too, because then you can try to think about what's actually happening. Yeah, so the oil line goes down if you electrify cars. That makes sense, right? So we're gonna be replacing gas burning cars. And be careful with the terminology here. Like gas burning cars means gasoline, which is a derivative of oil. So that's different than natural gas, which is CH4, which is methane. So yeah, so the oil line goes down. And then what do you think is gonna happen to temperature? So if we, actually let's go, so here's some details here. Electric share of final energy transport. So in the business as usual case, we're starting here with just 0.5% of transport is electric vehicles. And they have this very slowly in the business as usual case, getting up to 20% of vehicles by 2100 are electric. But if I increase this to increasing by 3.5% per year, now my current scenario has it so that I'm at like 2/3 of cars, 67% are electric vehicles by the 2090s. And what has that done to temperature? So let's look what happened here. This is a nice button here. Reset policies, or no, not that one. This one, replay last change. So I can do this to kind of see what's going on. If I just click that, it will go back and forth. So when I incentivize electrification, oil goes down, that makes sense. But temperature doesn't go down hardly at all. It only goes down 0.1 degrees Celsius. So why is that? Yeah, so it's causing coal to go up. So think about why that is happening, right? So if I incentivize cars to switch from being gasoline burning to electric, then overall we're going to be burning less oil. We need less oil, but we're plugging those cars in to electricity, which still is coming from burning fossil fuels for the most part and coming from coal in most of the world. So that electricity, it seems kind of clean because there's no tailpipe right there, but it's still dirty in terms of CO2. It's just far away from you. You can't see it. So it causes, if you have more electric cars, you have more electricity consumption. And then that drives up the amount of energy being produced from coal. And so that essentially cancels out all of the gains that you would get from reducing oil. And in fact, we talked about at the very beginning of the class how coal is worse than oil in terms of the amount of CO2 it produces per unit of energy. So then that really hurts you. So electrifying the vehicle fleet, and we can actually even increase this more. So there's, in each one of these, you can kind of mess around with assumptions. So I'm gonna go in here. Maximum potential electricity, max electrification of transport. Maximum percentage of transport energy sources that can be electric. The default assumes that planes and ships, which represent 20% of transport energy, are not electrifiable. So I'm going to get rid of that assumption. So you can get up to 100%. And then go in here and max this out. So now we're close to 100% of transportation is electric by the end of the century. And we still only eliminated 0.1 degree Celsius of warming. And so if we want to have this actually make a difference, we have to combine this with another policy that shifts energy away from fossil fuel burning, right? So if we look at our Kaya graph, our carbon intensity of energy has not gone down all that much. And so what we need to do is let's tax coal at the same time. Now we're getting somewhere, see? So if we electrify vehicles and tax coal, then we're starting to move. But you can see now, when I tax coal, what does that do to the other sources of energy? Now we have natural gas popping up and taking some of that amount of energy, right? So this is what they call this is squeezing the balloon. That like you have a balloon and you squeeze it in one end and it just makes a bubble pop up at another end and you have to squeeze that down. Like that's kind of a nice visualization of what's happening. So then you have to, okay, go over here and tax natural gas as well. And so now things are going better. But what else could we do? So if we could increase energy efficiency, well, if we also put a carbon tax on top of this, look at that, then we start moving down below 3, and we have renewables just dominating our other forms of fossil fuels here. And so now we're really kind of creating a solution by combining multiple policies. But you can see, so like something that's interesting here is that if you look at, this is like each individual energy source by itself. But if we look at the total, if we want to see like the total amount of energy, then we want these area graphs that stack everything up. So then you can see at the top is how much total energy is being used. And so here we can see that energy use is still going up by the end of the century. But if we were to combine all these policies with increased energy efficiency, then we're starting to drive down total energy use. And if we did like building an industry efficiency as well, now we're combining, now we have these two things going on at the same time, where the increase in energy efficiency is reducing the total amount of energy being used, and we're switching over our energy that we do use from sources of energy that burn fossil fuels to sources of energy that do not burn fossil fuels or do not emit greenhouse gases into the atmosphere. So renewables are taking over more of that. So if we look at our Kaya graph again, we have this, we have the same increase in population, the same increase in GDP per capita, but now a larger decrease in the energy that is required for any given unit of GDP, and a very large decrease in our carbon emitted per unit of energy. So that's where we're starting to actually get major gains here and getting closer to the Paris Agreement goal of 2 degrees Celsius above pre-industrial levels. So here's our CO2 emissions drastically coming down here. So let's do one more, a couple more here. So I can always press the home button to reset my graphs. You should explore, there's so many different graphs in here. So home resets the graphs, and then this circle resets everything back to baseline. So in the Wizard and Prophet book, one section from the last reading was called Coal First. And so what that section was about was if we were to eliminate, basically the point is like the very first most important thing we can do to address climate change is to stop burning coal for electricity. And so let's see what happens if we do that. So instead of just saying very highly taxed, let's look at this in a little bit more detail. And let's look at this option of stop building new coal infrastructure. So I can press yes on that. And then year to stop building new coal infrastructure. So 2025, so that seems, you know, reasonable. We have, let's say, starting today in 2020, I'm the global dictator and I say, world, you have 5 years. And after that, no more coal power plants. They are banned. And from then on, you have to build other types of power plants. So we see that coal declines, but look at our temperature. We went from 4.1 in 2100 to 3.6. So that's pretty good. It's better than a lot of things that we've been seeing, but it's not that great considering kind of how drastic a measure that is to say no new coal power plants. And I think that's one of the insights here, is that even if you're to do something like burn or to ban all new coal infrastructure, you just have to think about the time lags in the system. That like a coal power plant is there, once you build it, it's there for decades and decades. So it's there 30, you know, has a lifetime of like 30 years to 50 years. And so even banning all new coal infrastructure means that you still have coal producing electricity out into the 2060s, 2070s. And all of that CO2 just accumulates in the atmosphere and causes warming for decades and decades and centuries afterwards. So the time lags are so important and what make it so hard to reduce the amount of warming by the end of the century. And so we can even add on top of this coal plant accelerated retirement. So increase the annual retirement rate of coal plants used for electricity. Each percentage adds to the average annual rate of retirement. An increase of 5% would be significant. So that means that I'm going to say, okay, no new coal plants can be built after 2025. And the coal plants that do exist, I'm going to start taking them artificially offline, like faster than they would be otherwise. So then if I do that, then I'm starting to squeeze down this line even further. And we see that we have energy demand from coal getting down, but it still takes a long time, and it still means that it's not by itself going to solve climate change. So that might be one of the most important things we can do, and they talk about that in the book, and I think that it's a good, reasonable argument, especially considering, as we talked about, that coal has all these negative effects on human health because of air quality issues apart from CO2. So it's good to ban coal from that perspective, but it's not by itself enough. So I think that's actually that's what kind of the point of the assignment and the point of this calculator is, that there's not just one thing that's going to solve climate change. It requires a combined policies from all sorts of different directions. So like combining, you know, reducing coal with increased energy efficiency, with electric transportation. You need kind of the war on all fronts going at the same time. Okay, so one more here. If I do highly subsidized renewables, what is going to happen? So highly subsidized renewables. Here's our renewables is green. When I highly subsidize it, meaning that I'm making it artificially cheaper, so people want to consume it. So the government is making it artificially cheaper. It's no surprise that the renewable line goes up, right? And it does displace some coal and some natural gas. But again, it's like, okay, we're highly subsidizing renewables and we're only getting 0.2 degrees Celsius removed from our global warming by the end of the century. And like, why is that? And so another way, again, to look at this is if you look at these sources of energy by area. And so then that's going to show you the total amount of energy consume. So in 2020, we're at about 600 exajoules of energy per year. And then we're up over, so we're over doubling it by 2070. And then, you know, at like 13 or above 1400, more like 1500 exajoules of energy by the end of the century. So if I subsidize renewables, look at what that does. This is really important. I'm making it cheaper to have renewable energy. And overall, what that does is it increases the total amount of energy being used. So you get some of a temperature benefit because you're using renewables instead of some coal and some natural gas. But overall, because if you think about like in economics, that if you reduce the price of something, demand increases. When I artificially reduce the price of renewables, the economy, as far as this model is concerned, just says, oh, look, here's like another source of cheap energy. We're just going to use that. And it doesn't actually reduce the amount of energy. It increases the amount of energy that's used overall. And so I've heard this called adding pasta to salad. So like if you're on a diet, you want to replace your pasta with salad. You don't want to just add salad to your pasta. And so when you subsidize renewables by themselves, it's like just adding salad on. And so you want to replace the pasta. So you need to also combine that with reducing coal, oil, and natural gas, and then you're reducing the total amount of energy used. But when you do that, there's a trade-off. The trade-off is it increases the cost of energy. And so it can increase it by quite a bit the more you're getting down with temperature. So there's a real trade-off there, which is why it's been so hard to solve climate change. We've had like 25 straight years of the international community coming together and the countries negotiating, and we haven't made a lot of progress because there are real trade-offs here with the cost of energy. That it increases the cost of energy.